Good evening, everyone. Thank you, David, for the very kind introduction, and thank you to everyone for being here. And I'm hoping to give you an overview of this exciting field that is quantum computing. It's a little bit of a difficult task because it's a it's a field which has exploded recently, and it actually there is lots that we could talk about, and of course we don't have time to talk about everything. Okay, so why all the buzz? So you might have noticed that recently quantum computing has been in the media. So in February 2003, it actually made the front page of Time magazine. I read that article. I didn't find it very instructive. You learn about the major major industrial players. You learn about some curiosities, but didn't learn much. It has also been now since a long time also in more specialized media. This is Physics World. That's the magazine of the Institute of Physics in the UK, and that was 2021. They had an issue entirely dedicated to quantum technologies. Okay, let's try to set the scene. And so when we talk about classical physics, we all know what we're talking about. That's the experience that we have every day. So I actually, when I wanted to come up with words describing it, I found it really boring because that's what we know from everyday experience. I chose billiard balls for me, a typical example of object that behave classically and are very well described by Newton laws. It also shows maybe a little bit of a wasted youth, but that's a different story. On the other side, quantum physics. And somehow this is kind of words that probably will come to your mind. We are talking about probabilities instead of a deterministic theory, wave functions, superposition, interference, and don't worry about the equations. Classical physics, Newton 2, quantum physics, Schrödinger equation. And just quickly, that picture up there is actually an actual measurement, and that's an interference pattern of electrons going through two narrow slits. So that's an actual experiment. And so interference, particle wave duality, and basically quantum superpositions are at the core of quantum physics, as we'll see today. Okay. I wanted to give a definition about quantum computing, and I kind of didn't. I first went to some of the textbooks and took a really textbook definition, but then I chose this one. And the reason why I chose this one is not for the definition itself, but for the source. That's Amazon Web Services. So that's a company that is already selling quantum computing time. So you can go there and buy quantum computing time on different quantum processors that are available, like IBM or IonQ and IBM, IonQ and others. So yeah, it's not a bad definition. It's a multidisciplinary field, and it comprises aspects of computer science, physics, mathematics, and that utilizes quantum mechanics to solve complex problems faster than on classical computers. And the field of quantum computing includes hardware research and application development. I think you cannot give an introductory talk on quantum mechanics without a quote of Richard Feynman. And Feynman had an intuition back at the beginning of the 1980s that quantum mechanics can be effectively used to do computation and to simulate nature. And I actually will read this also because it's the only opportunity I have to use by golly because it's usually something that I would never say, but I can say it when I read this quote. So nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy. So that was Feynman in 1981, and that's what I would consider kind of the beginning of the field, this intuition that using the laws of quantum mechanics to do computation could be much more efficient in simulating nature. So I would like also to, before we get into the details, I would like somehow to convey a little bit of the excitement of the field. And I decided that I will let John Preskill's word do that for me. So he's talking about a frontier, and he's saying, I'm drawn to this field because I feel we are now in the early stages of exploring a new frontier of the physical sciences. What we might call the complexity frontier, or the entanglement frontier. This new frontier, while different than the frontier of particle physics or cosmology, is very fundamental and exciting. Now, for the first time in human history, we are acquiring and perfecting the tools to build and precisely control very complex, highly entangled quantum states of many particles. States so complex that we can't simulate them with our best digital computers or characterize them well using existing theoretical tools. And that's really exciting. So we have dealt with quantum systems for a long time. If you think of a superconductor, that's quantum mechanics that manifests itself. But here we are talking about controlling quantum states with such a precision that we can use them to make computations. And that's really for me, that's where the excitement is. Okay. I don't know if epistemological map is the right word for that. It's something that, for me, it's a little bit for myself to basically understand which different parts of knowledge contribute to quantum information and quantum computing. So, of course we have physics. Basically, quantum mechanics is physics, and so physics is part of it's crucial to quantum computing. But we also have computer science, so theory about algorithms, general models of a quantum computer, a universal quantum computer, and we have information science. So basically, what is quantum information? What is quantum communications? What are quantum channels? And all these things. And all this part is the more mathematical part of quantum computing and quantum information theory. And then, of course, there is this side, and that's basically physics and engineering. And basically, physicists they design and characterize systems that can be used as quantum hardware, for quantum computing. They want to basically discover new materials which are more suitable for quantum hardware. They try to minimize noise and errors which are very detrimental to quantum computing. And then, of course, you need to put all these bits together, and you need to have a quantum architecture. And this is going to be quite complicated, so you will have a lot of electronics also that needs to be designed, and often this electronics has to be at very low temperature, and so that's where the engineering comes. So that's a little bit for me, the map of all the knowledge that sort of contributes to quantum information and quantum computing. Okay, so what's the plan for today? So the plans for today is that I will start with giving a bit of, explaining what qubits are, quantum bits of information, and what we do with qubits. Then we will discuss what are quantum computers good for, and then there will be some part about how physical realizations of quantum computers, and at the end there will be conclusions. Okay, so if we think about classical information is stored in bits. So, and these bits can have either one or two states, 0 or 1. So if you think of any digital computer that you have basically what it deals with strings of zeros and ones, and it does operations of zeros and ones. And these classical bits, they can be either 0 or 1. So if you allow me a comparison, you can think them of as a coin. And so your state of your bit is head, which in this case will take for 0, or tail, which in this case takes for 1. I'm actually realizing that I haven't seen a coin for a long time after COVID. Maybe. Anyhow, so now quantum bits obey quantum mechanics, and one of the crucial things of quantum mechanics is that systems can be in a quantum superposition. So basically what it means in the coin example is that the state of a quantum bit can be a superposition with coefficients, so these are numbers, of head, our 0, or tail. And don't worry about this weird symbol. This is called a ket, and it's a notation that was introduced by this man here, by Dirac. And but for us, what it means, it just means the quantum state 0, the quantum state 1, or the quantum state head. So we'll use this just as a notation. And so what is here? You will see that in my slides there will be blobs in greens, and blobs in greens are somehow the message of the slide. So classical bits, 0, 1, quantum bits, superposition of states. Now you could ask, why is it so? And I see lots of my second-year students here, and they have asked this question a lot of times. And you can go down a rabbit hole by asking this question, and the only answer that is probably, for me, the only legitimate answer is because nature behaves like this, and because this theory has been tested and retested, and it actually works, and it predicts outcome of experiments. Okay. So I'm going to apologize for this. There is a little bit of maths on this, but there will not be much, and I'll talk through what is important. So okay, so we said that if I have one quantum bit, it can be a superposition of 0 and 1 with these coefficients alpha and beta. So I don't know what is the general sort of, I see many scientists here, but probably not everyone is a scientist. So these alpha and beta are in general complex numbers. But if you haven't seen complex numbers, that doesn't matter. Just think them as real numbers, alpha and beta, these coefficients. And in order to characterize this state, what I need to know is what these alpha and betas are. So I just need to, so if I want to describe these states, I need to know what alpha and betas are. So what I can do is I can, write them down in a column, and I say that I can represent these quantum states by this column. That's a vector, and so that's my description of this quantum state. So again, if you haven't seen vectors, this doesn't matter. It's just this. We just need to keep track of those two numbers. Now, these numbers are related to the outcome of experiments, and so these numbers here are alpha if you do modulo squared, or let's say if you square it, it gives the probability that if you do a measurement on your system, you get a 0. And this one, beta, conversely, gives you the probability beta modulo squared. Again, if you think them as real numbers just squared, this gives the probability of measuring 1. And of course, since I have only two possible outcomes, the two probabilities have to add up to 1. So these alpha and beta have these constraints, which is a very physical constraints. The probability of all the outcomes have to add up to 1. Now, Okay, now this don't work. So for those who are mathematically expert, you will probably see that I can write these coefficients here, alpha and beta, in a different form, and in this way I make sure that their sum is 1. It doesn't matter. For all the others, let's think that we can represent these numbers as a function of two angles that theta and phi. And theta goes from 0 to pi, and phi goes from 0 to 2 pi. So this state can be represented by these two angles, theta and phi. And we can visualize then this state and say, well, if I have a certain value of theta, that's my state, and a certain value of phi, this state is basically, I can describe this, I can visualize this as a point on a sphere. And if I change theta, the point changes on the surface of the sphere. So let's say that I choose one particular state, kind of one where these coefficients are the same, both 1 over square root of 2 and 1 over square root of 2. This would correspond to choosing theta equal 90 degrees, so I'm in the xy plane, and phi equals 0, so it's this particular point on the sphere. What is the message here? The message here is that if I had a quantum bit, a classical bit, sorry, there were only two possible states, 0 and 1. Now, any point on this sphere is called the Bloch sphere, describes a possible qubit state. So now we have many more states that are possible states of our system. Okay, that's good. We have states, we have qubits. Now we want to do gates. We want to do operations with them. And so let's start again with classical bits. So if I have a classical bit of information, we said it's either 0 or 1. There is only one meaningful operation that I can do on a classical bit of information, and I can invert it. And that's called the logical NOT. So if my classical bit is 0, then the output is 1. If the input is 1, then the output is 0. That's called the NOT gate, the classical NOT. Now let's try to do it, and so that's the symbol that we usually use. And now let's try to do the same with a qubit. And so let's introduce the quantum NOT gate, which is often, the symbol that is often used is X. And that's the circuit symbol for the NOT gate. And so let's say that we have this quantum state 0, that is a quantum superposition of 0 and 1. And what this NOT gate does, it transforms the 0 to 1, it inverts it, and it transforms the 1 to 0. And it actually acts linearly, because basically you see that it does this for this linear combination. So in the same way that we decided to represent the state by a vector, alpha, beta, we can represent this operation by a matrix. Now a matrix, again, here, just take it as a collection of 4 numbers. It's just a discrete, instead of showing you a truth table, I write this in this way, and basically then the math that I can do is that if I multiply this matrix to this vector, for those who probably have done high school a few years ago, I think it was covered, matrix and vectors in. If you do this, you basically find that the two coefficients are swapped. So that now the coefficient in front of the state 0 is beta, and the 1 is alpha. So what is the message here? The message here is we can describe quantum operations by 2x2 matrices, and they act linearly, and so the NOT gate, for example, that's the operation. That's what the NOT gate does, and that's another way to represent it. And if you are not familiar with linear algebra, it doesn't matter. Because that's already enough. That's already telling you what's the operation of the NOT gate. Is this the only gate for qubits? Actually, not. We can do many other things. We can do, for example, we can define another famous gate. Just as an example, it's called Hadamard gate. Don't worry about the matrix representation, but just let's have a look at the effect. If I have a qubit that is in the 0 state, and I apply this gate, it creates a superposition with equal coefficients. If I apply the gates to the qubit in the state 1, it also creates a superposition with equal coefficients, but here there is a minus sign. So what is the message here? The message here is that 1 qubit gates are described by 2 by 2 matrices, and actually these matrices need to be unitary. Don't worry about the maths here. This requirement, it means that the probabilities of the outcomes had to add up to 1 afterwards, and that translates to a requirement on the matrices that are allowed. So, because you see that if I take these coefficients and square them, they still add to 1. So actually, for classical bits, only one operation was possible. For quantum bits, any 2 by 2 matrix, any unitary 2 by 2 matrix describes a legitimate 1 qubit gate that can be actually implemented. Okay. We cannot do, of course, if we only work with 1 qubit, well, we can. It's not very powerful computer, right? If you have only 1 bit of information, it's not really a powerful computer. So we need to think about many qubit states. And so if I have 2 bits of classical informations, okay, so these are all the possible states of 2 bits of classical information: 0, 0, 0, 1, 1, 0, 1, 1. If I do quantum mechanically, it works exactly as before. Now I have this state here, means qubit 1 is in 0, and qubit 2 is in 0. That's qubit 1 and qubit 2. And here 1 means qubit 1 is in 1, qubit 2 is in 0, and so on and so forth. But quantum mechanically, that's what quantum mechanics does, is we can write this as the generic state is going to be a superposition, a quantum superposition of those 4 states. And this, again, I need to remember these 4 amplitudes, these 4 coefficients, so I might as well put them in a vector, and that's my description of the state. Now, when you start dealing already with 2 of those quantum bits, things starts getting intriguing quite quickly. Because, among all these ones, I can choose, for example, a state like this, which is a superposition of 0, 0 and 1, 1. This innocuously looking state, which somehow seems like, it's there, it seems like a simple and innocent, it has caused a lot of trouble. That's the kind of state that somehow made Einstein think that quantum mechanics was wrong and that could be hidden variable theories and so on and so forth. This is an entangled state, and it's actually this particular state is given a name. It's called one of the Bell states, but that doesn't matter. Why is it particular? So now let's imagine, and I will jump in front of the screen here. Let's imagine that I do a measurement on the first qubit, this one. Okay, if I do that measurement, I will find 0 or 1 with equal probability, 1/2. And so I do that measurement and I find either 0 or 1. Then I re-prepare my state. I start back and I redo the measurement again. And I get again at 0, 1. And so on and so forth. I write a list. And my list would look as a random list of 0s and 1, like if I had thrown a coin. Now I'll do a different experiment. I'll do a bit more. So I measure qubit 1, and I record in one list what I get, either 0 or 1. But immediately after measuring qubit 1, now I measure qubit 2, without preparing, just immediately after. Now, if I have found that 0, quantum mechanics is a bit weird. If I have found that 0, the state will collapse into this, because this is where 1 with the 0. So, if I found that 0, the second measurement will give me a 0. If I measure, for the first measurement I get of the first qubit, I got a 1, then I end up with a 1. So now I record all my measurements also of qubit 2. And measurements of qubit 2, they will look again as a random list of 0s and 1. If I compare the two lists, I will have a perfect correlation. Every time I measured 0 in qubit 1, I measured 0 in qubit 2. Every time I measure 1 in qubit 1, I measure 1 in qubit 2. And this what freaked out Einstein a little bit, because he said, if I take these two qubits and I put them very far apart, how is it possible that when I measure one, the other one, the measurement of the other one is determined? And so that's what Einstein didn't like, but that's exactly how nature works. And so, again, what is the message here? That the Bell states are entangled, maximally entangled. And John Bell, I think he was an Irish theorist. He proved actually that the measurement correlation in these states are stronger than you can get in any sort of classical theory, any hidden variable theory. I don't want to go too much into this because it's an entire new talk about Bell inequalities, and for the students here, you will actually check this in third year on a quantum computer. So you will do a test of this Bell test on a quantum computer in third year.
Is that what Einstein referred to as spooky action?
Yes, that's exactly what Einstein.
And this could actually apply even if they're separated
Yes.
by an enormous distance,
Yes.
by billions of years.
Yes, but then it was proven that this cannot be used to actually communicate between the two people that had the two qubits, so that they didn't. So that's what is also known, just to make references to, as the EPR paradox, Einstein, Podolsky, Rosen. Okay. Yellows are also often quotes. Here there is another pioneer of quantum mechanics, and Schrödinger described entanglement as the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Okay, I want to go quickly about this. Of course, in order to make a quantum computer, we only need to have operations that act on two qubits. So 1 qubit gates are not enough. We need at least one 2 qubit operation, 1 2 qubit gate. The one that it's enough is this so-called control knot. And this is actually quite easy. Basically, what it does is you have 2 qubits, and 1 qubit is called the control qubit, and the other one is called the target qubit. So depending on the value of this one is negated. So let's have a look how it works. So if the control is 0, then if the control is 0, then the target stays the same. So 0 goes. If the control is, okay, again, control is 0, I don't do anything on the second one. But if the control is 1, so the second one gets inverted. So 1 0 goes to 1 1, and 1 1 goes to 1 0. And basically, this can be described by matrix, doesn't matter, I think at this point. But what is important is that if I implement such a gate, any multiple qubit gate can be composed from C0 gates. And that's what's done in practical quantum processors. And 1 qubit gates. Okay. Yes, I stop with 4 qubits, I promise. Now if I go with 4 qubits, I can have, I can have a state where qubit 1 is in 0, qubit 2 is in 0, qubit 3 is in 0, qubit 4 is in 0, and then I have 1, 0, 0, 0, 1, and yes, you got the gist. And since we are quantum, my generic quantum state is a linear superposition of all of those. And so if I want to specify which states I am, I have to tell you these 16 numbers, which are in general complex. So I have to give you 16 amplitudes. Now let's generalize this. Let's go to n qubit, where n is an integer. And now, so these were 4 qubits, and I needed 16. 16 is 2 times 2 times 2 times 2 is 2 to the power of 4. If I have n could be, I don't know, 50 or whatever, I need to specify 2 to the power of n coefficients. I say, okay, that's not too bad. You know, if I have 4, I need, so if I need 16, if I have 5, I need 32. Yeah, that grows quickly, as we learned from COVID about exponential growth. That grows so quickly that if I want to describe a generic state of 300 qubit, I need 2 to the power of 300. Okay, that's a number that I cannot even think. And if you try to get it in sort of powers of 10, that's 10 to the 90. This is 10 to the 90 complex coefficients. Now, if you check what the estimate of number of atoms in the observable universe is 10, I think, to the power 80 or 85. So there are different estimates. So this is a huge number of numbers, and so we can't do that. And that's what Preskill was referring to by saying that even our best class digital computers cannot simulate a quantum computer with a modest number of qubits, like 300 qubits. The other thing and that's where Feynman comes. Let's go back to this. Nature is keeping track of those coefficients for us, right? It's like nature has a notepad and somehow is able to keep track of all these coefficients, do time evolutions on states like this. And so that's the idea of Feynman, is why can't we use this power of nature for simulations? Why can't we use this quantum, the fact that that we have these superpositions for simulation? So the message here, it's practically impossible to use a classical computer to simulate a medium-scale quantum computer. Okay, why quantum computers? So already somehow it is clear that if you have a quantum mechanical system, things grow very quickly, and they become and so it becomes impossible to describe it. And there are problems. And so often what we do as physicists, we do approximations, and often we get away, not all the time. So there are situations, for example, when we try to design new materials, when we try to describe certain quantum, certain chemical reactions, when we want to describe complicated new drugs, where we actually need to describe basically we need to sort of simulate quantum mechanics. And these are very challenging problems, and where approximations might not be sufficient, and that's where quantum computers are really, really good. So we can use quantum computers to describe, for material design, computational quantum chemistry, drug discovery. And so here the message is, if I have a system where we have lots of electrons, like you can have in a complicated sort of compound, the computational resources, time, grows exponentially with the system size, with the number of electrons. And as everyone, doing material science knows, if you try to do exact computations, you are often limited to very few numbers of electrons. Okay. How am I doing with time? Because I lost a little bit track. Good, thank you. Okay, so I want to discuss another problem, because this was one of the first problems that somehow where quantum computing has an advantage with respect to classical computing. So there are problems which can be solved much more efficiently by a quantum computer than a classical computer. That's my statement. And one of those is integer factorization. You could think, oh, that's really boring, right? It might be very boring, but it's very important. It's very important because whenever you pay with your credit card on the internet, you are using an algorithm that is called RSA. It's a public key cryptography algorithm. That's what makes sure that your details of your credit cards don't get stolen. So it's actually a really important problem. And it's about integer factorization. So what is at the core of this type of algorithms is that if I take this n is a large integer, and this integer is just the product of two prime numbers. Let's make it small. Let's say that these two prime numbers are 3 and 5, and the integer here is 15. Now, with such a small numbers, it's easy to multiply 3 and 5 and get 15, and it's also easy to go back. But if this n is very large, then it's easy to, if you know the prime numbers, to get the large p, the large n. So if you know p and q, it's very easy to get the large n. But if you're given just a large number and you are asked what are the prime factors, that's actually a difficult problem computationally. What does it mean difficult? It means that if you try to do it on a classical computer, the best classical algorithm goes with this formula. Don't worry about this. Just focus about this exponential. So it basically grows exponentials with the number n. So if the number n has b bits, this grows exponential with n, and that's what makes RSA safe. So you just take a very large number. That's your public key, and people cannot find the two prime numbers that gives this large number, because the resources to do that are not available. It would basically mean, usually the quality of your encryption is such that if you put all computers on the Earth for all the time that the universe has existed, they will not make it. So that's how it works.
Michele, sorry to interrupt. Now, that equation, that algorithm is probably pretty reasonable for a certain magnitude of natural numbers and left-hand.
Yes, that's.
If you say, let's say it worked reasonably well for numbers of the order of 10 to the power 400. But if you went far and away above that, will that algorithm become worse and worse, or just become better and better?
I think this one. So this estimate is actually given. This estimate is given for large values of b. So that's the order of magnitude. So it's an order of magnitude. So basically, what you think about it like exponential in n.
Yeah.
So, however, Shor proved that there is a quantum algorithm that can do this as the number of bits to the power of 3. That's polynomial time. Just to give you to show you what it means. I think we should all have become expert about exponential growth with COVID. So that's the classical algorithm, how it grows with number of bits. Notice that this is so-called log scale. So this is 10 to the power 7, 10 with 7, 1 with 7, 0, 10 to the power 17. And so that's the classical, and that's the quantum. And the quantum is since it's a polynomial, it's like a power of b. It just looks, pretty mild. So you see, if we get a quantum computer to do this, we can break RSA. Okay, so let's. Can you tell me? 35. Okay, so last 5 minutes, let's talk about how to make quantum computers. And in 2000, I think, David DiVincenzo, a scientist at IBM, came up with criteria for a physical implementation. So you need a physical system where you can describe, where you have well-characterized bits. So you have systems with 2 states, physical system with 2 states. You need to be able to initialize those states, to basically say at the beginning I want to be 0, 0, 0. You need to protect these states from, let's say, from noise, and you need to be able to keep these states behaving quantum mechanically. You need to be able to operate on those states, so you need a universal set of quantum gates, and you need to be able to measure the outcome. So that's the DiVincenzo criteria. Okay, physical implementations. So the first thing that we could think of, and I need to introduce another concept for those who are not physicists, is a spin 1/2. So electrons have a tiny magnetic moment associated with them. You can think of them as being some tiny compasses, some tiny magnets. And if you measure whether the magnet is pointing up or down in a given direction, it has only 2 states. And so that, in a way, spin 1/2 is a prototypical 2-level system. And so people thought, these two gentlemen here, Loss and Di Vincenzo, said, well, what about we encode 0 and 1 in this spin up and spin down of those electrons? Those are states that are, that's a two-level system, so it should work. And then they thought, we know very well how to do semiconductors, so, why we try to confine those electrons in some small paddles, we call them quantum dots in semiconductors, and we try to operate on them, applying voltages and magnetic field, and so this is proposals, and these are modern devices. It's very complicated. So all these fingers here, colored fingers, are sort of metallic gates to control the spins of these electrons. Across the ditch, instead, they somehow embrace this Bruce Kane's proposal, and the idea is, why don't we use the nuclear spin of a donor? It's a phosphorus donor. In silicon again, and that nuclear spin can act as a spin as a spin 1/2, and this was, of course, really, it poses a lot of problems because we need to be able to sort of put individual atoms in silicon with atomic precisions, and that's what actually they are doing in Australia. Other qubits, and that's there are superconducting qubits, and basically rely on two ingredients: superconductivity. Superconductivity, it's a state in which, if you cool down certain materials, you find that all your electrons, what they do is they pair together, they form Cooper pairs, and then all these Cooper pairs occupy only one quantum state, and this gives rise to all the wonderful phenomena that you see in superconductivity, like zero resistance. So we talk about macroscopic quantum coherence. And then another thing is they rely on Josephson junctions, and what this is just you take two superconducting wires and you separate them, or electrons, by a thin insulating barrier. And I don't want to go too much in detail here. I don't have time. But these are qubits that are realized, and I will describe only the simplest one. The simplest one is where you have this ring. It's called a flux qubit. You have a ring of a superconducting metal with 3 Josephson junctions, and basically your two quantum states are current clockwise, let's say 0, current counterclockwise 1. But that's one of the simplest ones. There are different type of qubits, and this is actually what is also being used in some of the commercial quantum computers. Okay, I am almost going over time, probably going over time. So there are already quantum processors available. And this stage of the technology, we called it NISQ, Noise Intermediate Scale Quantum. What do we mean is that we don't have that many qubits of the order of hundreds. And the other thing is we have errors, and so we need to do error mitigations. The system is small, so we cannot use powerful techniques which are like quantum error correction. And so we are still in this sort of infantry in this stage, but these computers have already been used they're already being used and I'll finish just showing what's on the market. So Google, it's a bit difficult to find information about what Google is doing. So all of this, both Google and IBM are using superconducting qubits. Google is a bit more secretive. And so the last thing I could find is that they had a quantum processor with 54 qubits. IBM, it's actually, it's a bit more open and makes much more releases. And the last quantum processor that they have is Osprey with 430 qubits. IBM actually now has a 127 qubit processor available to everyone online, only for a maximum of 10 minutes computing time per month, and lots of good resources to learn about quantum computation. And it's actually an excellent tool to teach quantum mechanics. there are other players. Intel, for example, is playing with this silicon qubits in collaboration with Delft. Microsoft is going a very different route, a route which will probably require another talk, because Microsoft is doing something that using some sort of strange materials which have so they're called topological qubits. It's a complete different kettle of fish. No time. There is another company, Rigetti, superconducting qubits, IonQ. They use ions, and they use levels of so quantum level of ions in a trap. IonQ is not the only one. Honeywell is also pursuing this route. At these links, actually, you can go and find what they describe how they do, how their quantum computers work and how big is the quantum processor and so on and so forth. Okay, I wanted to finish just saying that one of the good things with COVID was that we all were in lockdown and bored and not knowing what to do. So with my colleague Uli Zuliger, who's sitting here in the audience, well, we decided, why don't we learn how to use a quantum computer and use it in third year quantum mechanics? That's what we did, and now we use it routinely at Victoria University to practice concepts as quantum superposition, operators, measurements, entanglement, Bell's inequality, and that's actually, I have a few students here, so that's what you will await you in assignment 4. You will have to test Bell inequality on IBM quantum, worth quite a few marks. And it's actually really good fun. It's really good fun, and it's really good way to learn quantum mechanics and with really sort of like doing experiments. You're doing actual experiments. The first time I actually tested Bell inequality, I was like going, wow, really? I was so, I've been a pen and paper guy all my life, and suddenly, I was sending information to a small, tiny quantum chip that was sitting at the bottom of a cryostat at millikelvin temperature, and then I was getting data back, and I was really, I got goosebumps. I was like, yes, it didn't convince me to become an experimentalist. Anyhow, I'm sorry that I took a little bit of your time here. So, what I've tried to convey to you is that quantum information and quantum computation is a very fast developing multidisciplinary field. If you want to remember one thing, quantum superposition and entanglement are key features of quantum mechanics and quantum computation. And the other thing is that quantum computers are intrinsically faster than their classical counterparts, but for certain tasks. There will be tasks that are easy for classical computers, and quantum computers will never, it makes no sense for us to use a quantum computer. So it's only certain tasks. And the other thing is, this technology is already here. So you can go on IBM Quantum, register, and use a quantum computer. Thank you so much for your attention, and again, apologies for being a bit over time.